All right, guys. Today we're going to have probably a pretty quick video on the perpendicular and angle bisectors and the theorems that come along with it. This is kind of stuff that maybe you won't be slightly familiar with it, even if you don't know it already. But let's go ahead and take a look at the perpendicular bisectors first, and then we're going to look at the angle bisectors afterwards. So, our perpendicular bisector theorem states that if a point is on the perpendicular bisector of a segment, okay, the perpendicular bisector of a segment, then it is equidistant to the endpoints of the system. And I kind of blew over this on accident. So equidistant is exactly what it sounds with. Equal, distant, distance, means it's equal distance from two objects. So depending what the objects are, whether they're points, lines, anything, they're equal distance. And then what the perpendicular bisector is just this line. It bisects a segment perpendicularly. That's all that is. So we have this relationship, kind of our given, and this is our result. So if a point is on the perpendicular bisector of a segment, so I know those lines have to be perpendicular, and it also has to bisect, so AY and YB have to be equal to each other, or congruent to each other, then it is equidistant from the endpoints of the segment. So XA and XB, which are the red lines, those are congruent. Okay? And the converse is true. So if a point is equidistant from the endpoints of a segment, saying that if this line and this line, this one and this one are congruent, then this XY is perpendicular to YB, and YA is congruent to YB. So I don't like how they didn't put the tick marks on there, but that is true, as well as up here. Okay, so this means we could do a couple things based on what we are given inside of our problem. So if we scroll down here, this example is taken from 293. There is another example where it spells everything out as well. This is just like a sample problem essentially. Let's take a look at what we got. So I want to find what these lengths are. I have no real information about those lengths, whether they're congruent or not. So that's what I want to find out. But I do see that I have a perpendicular bisector because I have a line that is perpendicular, and this line PR is bisected. Let's note, or let's figure out, or let's take a look at how we know this. So this would be our midpoint because the two sides are congruent. So if this is the midpoint, then that means that this line QS is bisecting PR. So now what does that mean? If we go back up here, I have that our line is perpendicular and that these two sides are congruent, thus meaning that this line has to be congruent to this line. So I know that's a lot of green going on. But, so PQ, oops. So now we know PQ, the line must be congruent to QR. Now we can just substitute in. So PQ is 3n minus 1. Because now we're dealing with measures, we can switch to equals 5n, oops, it's got to be minus 7. And now we just do some math. I'm going to take more than one step because some guys were confused. So negative 3n on each side. So we're going to have negative 1. We're going to be left with a 2n minus 7. So now what I'm going to do is add 7. So 2n is going to equal 6. So n will equal 3. So now plugging this back in, if n is 3, we're going to have 3 times 3 minus 1, or 8. And then we're going to have 5 times 3 minus 7 15 minus 7, and 8, which makes sense because they are congruent. So them having the same measure makes sense. Now let's go ahead and look at angle bisectors and the angle bisector theorem as well as the converse. So the angle bisector pretty much says the same thing. If a point on the bisector of an angle, instead of a segment this time, it's an angle, then it is equidistant from the sides of the angle. So we have a bisector of the angle. We have a bisector of the angle. It is equidistant, these two measures. So we see APC, this angle, that angle, they are congruent. We know that AC and BC are going to be congruent, equal as well. So now we're talking about the converse. The converse just says it backwards. So if we have this AC and BC that are congruent, we do now know that APC and BPC are congruent as well. So, excuse me, it's essentially just the opposite or the converse of what the angle bisector theorem is. What's up?
Do you have any colored tape?
No, I'm sorry about that. I don't. Okay, sorry about that. Some of the chart guys were asking me a question. All right, so let's go ahead and do a problem with these. It's going to be quite similar to our perpendicular bisector. And once again, so this example is a sample problem. There's another one that looks like it just on 295. So let's look at what we got. In the problem, we want to find the measure of these two sides. Now, I know that these two angles are congruent. This BCF, so BCF, and we could say DCF. They are congruent. So if those two angles are congruent, I know that FC bisects angle BCD. So this line bisects the bigger angle because these two little ones are congruent. Now I also know, and I should have been more clear about this, these are right angles. And there's a reason why they have to be right angles, and I'll go over that in a second. But, so now we know that these two measures are going to be congruent. So we can set that up. We know BF is going to be congruent to FD, meaning their measures are going to be equal. So we're going to have 6x plus 3. So we go to 4x plus 9. I'm going to subtract, and we're going to be left with this. Now I'm subtracting 3. And once again, I'm going to get x is equal to 3. Plugging it back in, I'm going to use a different color. So we're going to have 6 times 3 plus 3. Oh my gosh, 6 times 3, what is that, 18? Plus 3, so we're going to get 20, oops, not 12, 21. 21, and then 16 plus, oops, not 16, we're multiplying by 3. 4 times 3 plus 9, so we're going to get 12 plus 9, so 21. That makes sense that these two measures are going to be congruent based on our angle bisector theorem. Those two lines are going to have equal measure. Now, so there's a stipulation in these, as you can see, that these angles are all right. So this is because of the quote-unquote distance to a line, or distance to a line from a point. So this is just a notion. If I have a line out here and just some random point, the shortest distance is going to be straight to that line. It's not going to be out here. It's not going to be there. Not going to be there. It is going to be straight to the line. And a fact about that is that creates a right angle. So anytime we talk about a distance to a line, as we do up here, we're going to be dealing with a right angle. So that is something that is necessary. And when you guys are doing your problems, you're going to see that all of these sort of diagrams like this are going to have those right angles. So that is distance to a line from a point. So that's something important that you guys need to know. Other than that, so this is going to be Tuesday night's video. Wednesday, we're going to be doing some practice. I hope you guys have a good rest of your night. And we'll see you.